Assalamualaikum and hi everyone. I am Nazihah binti Muhammad Ali from UC Putra Malaysia. Today I would like to share with all of you about research that we have done regarding modified multivariate cumulative sum control chart based on robust estimator. First of all, let me introduce the most established and well-received multivariate statistical control chart by the researchers. The first one, we call it as Hotelling T-square control chart. The second one is multivariate exponentially weighted moving average or MUMA control chart. And the third one is multivariate cumulative sum or MQ sum control chart. We use multivariate control chart when there are more than one quality characteristic that need to be monitored on the process. And most of the quality characteristics in a process are highly correlated. MUMA and MQ sum are the alternative to the Hotelling T-square when we want to monitor the small shift or the moderate shift of the process mean. The classical multivariate control chart is simply based on the sample mean vector x bar that represent the center of quality characteristic and the sample variance covariance matrix S that represent the dispersion of data from the x bar, from the mean. These two parameters are known to be sensitive to outliers or shift and will be greatly influenced by their presence. Due to this problem, a modification on the classical control chart based on robust statistics are done by many researchers and they showed better performance as predicted. One of modification have done by Abu Shawish and Abdullah in 2001 when they developed a new robust Hotelling T-square for bivariate data using Hodges-Lehmann estimator as location estimator and Shamos-Buchanan estimator as scale estimator. In this research, we modified on the classical MQ sum control chart using several robust estimators. There are two robust location estimators, namely the modified one-step M or MUM estimator and the Hodges-Lehmann or HL estimator with the median absolute deviation, which is MED-N, as the robust scale estimator. The performance are then compared to the classical MQ sum control chart for bivariate data of the normal distribution under different conditions that include proportion of outliers and process mean shift. This is the classical multivariate Q sum control chart. Let Xj here be a sample from multivariate normal distribution with mean zero and identity covariance matrix IP, where P is the number of quality characteristic. The multivariate Q sum statistic is as follows, as equation 1, 2, and 3, and the covariance matrix S as follows, where the variance and covariance of Xj as equation 4 and 5 respectively. Next one is the MQ sum control chart using modified one-step M estimator or MUM. The first approach uses the MUM as the location measure to replace the usual mean vector in the classical MQ sum control chart. The MUM estimator, as proposed by Wilcox and Castleman in 2003, is defined as equation 6, with the characteristic variables as equation 7, 8, and 9 respectively. And here they use constant K 2.24 so that the efficiency is good under normality, especially for the small size. As mentioned by Wilcox and Castleman in 2003 and Said Yahya et al. In 2006. Wilcox and Castleman in 2003 also found that the efficiency of MUM estimator is equal to 0.9 for M equal to 20 when K equal to 2.24. Hence, the value of K equal to 2.24 will be used throughout this study to MUM approach. To construct the new robust MQ sum statistic, the MUM will replace the usual mean vector in the classical MQ sum statistic. So we get this equation 10. And the next one is the MQ sum control chart modified by using Hodges-Lehmann estimator. So we can find out the computation of Hodges-Lehmann estimator shown as below. This one by Abu Shawish and Abdullah in 2001 and Majid Harun and Midi in 2010. This one by equation 11, 12, 13 and 14. The next one is MQ sum control chart using median absolute deviation estimator, which is at MED-N. The P times P covariance of MED-N is denoted as S-MED-N. And first compute the diagonal element of the P times P covariance matrix, which are the sample variances of each variable, which are represented by MED-N square Nj by equation 15. According to Abu Shawish and Abdullah 2001, the remaining element of P times P covariance are calculated by using these 4 steps. The first one, compute the MED-N. Second, compute the Spearman. And the third one, compute the MED-JG. And the fourth one, to find the P times P covariance matrix by equation 17. Hence, we have the formula for robust MQ sum control chart as follows, as equation 18 and 19. To monitor the performance and the capability of this new robust MQ sum control chart, the probability of detecting mean shift are calculated. For the probability of detecting mean shift, the higher the probability, the better the chart performs in detecting mean shift. Here we set the values of quality characteristic P at 2, 3, 5 and 10 together with the subgroup sizes M equal to 30, 50, 100 and 400. And here we use 5 level of mean shift, which is mu1 that are 0.5, 1.0, 1.5, 2.0 and 5.0 with proportion equal to 0.1. And the upper control limit UCL is required since the lower control limit is always set at 0. For this study, the simulation method is utilized to get the UCL of all MQ sum as done by Alfaro and Ortega in 2009. And the simulated UCL of all control chart is obtained by generating 5,000 data set of subgroup size M such that Xj from in control condition. The false alarm is set at alpha equal to 0.05. And to retain alpha equal to 0.05, the 55th percentile of the recorded maximum values are declared as the simulated UCLS. So this is the result. Figure 1 represents the performance of the investigated chart in terms of their probability in detecting shift when the quality characteristic P equals to 2. When small mean shift occur, the C-square HL with MED chart appear to have the best performance for all subgroup of size M, and followed by the C-square MUM with MED chart, and lastly the classical chart. Figure 2 represents the performance of the investigated chart for various mean shift at P equal to 3, and this one shows the C-square HL with MED mostly showed better performance than other two charts. The next one represents the performance of the control chart with P equal to 5. The pattern are observed to be almost similar to P equal to 2 and P equal to 3, with C-square HL with MED control chart produce the best performance, followed by C-square MUM with MED and the classical control chart. And the last one, figure 4, represents the performance of the control chart when P equal to 10. Figure 4a, b, c illustrate the case of mild and moderate contaminated with the mean is shifted at mu1 equal to 0.5, 1 and 1.5. The two robust control chart perform better than the control chart, the classical control chart. There are downward trends as the value of M increase for all control chart. So this means that the bigger the subgroup size, the smaller the probability of detecting the mean shift. The presence of mean shift or outlier can be cause misleading conclusion of the control chart if one use the classical approach. So as the conclusion, C-square HL with MED control chart has the best performance among these three control charts when the mean shift happen to present in this data set. Besides, C-square MUM with MED and C-square HL with MED also perform better than the classical control chart for smaller mean shift. This is the reference, and thank you.